Thermophysics class, continuing from yesterday, we're going to be introducing the idea of the microcanonical ensemble. I'm going to go through several of the slides in the slide deck, but I'm not going to read everything to you. I'm just going to hit the high points and focus on what you should be focusing on as you read them through. The basic idea, though, is we consider a large number of replicas of our system. Each is subject to the same physical constraints, and the state will be characterized by things like temperature, pressure, and volume, or maybe internal energy, volume, and particle number. What we want to know is the probability of some value of a parameter. In other words, that turns out to be the probability is what fraction of the replicas assume some particular value. So we typically going to have some partial knowledge, and the system can only be in states that's compatible with the information that we have, and we call those the accessible states. There are states which the system can't go into because of the knowledge that we have. So we use ensembles distributed over accessible states, and we'll determine a method of finding the probability that a system is in one of the states, and we'll use what we call the microcanonical ensemble. A microcanonical ensemble is a method of representing isolated systems in equilibrium. An isolated system is a system that can't exchange energy or particles with its surroundings. That's why it's isolated. In other words, its total energy is always conserved. So, for an isolated system, when it's reached equilibrium, the probability of finding the system in some state is independent of time. All of the macroscopic features of the system are also independent of time. And our fundamental requirement is one that we've already stated: equal a priori probabilities. So an isolated system is equally likely to be in any of its accessible states. The corollary of this is, if an isolated system is not likely to be not equally likely to be in any of its accessible states, then it's not an equilibrium. Equilibrium, by the way, is a macroscopic concept, not a microscopic concept. So we need to apply these ideas to a simple system. What we'll do is we'll consider n molecules of a one-component system, meaning there's only one chemical species present. The system's totally isolated. That means that its internal energy E, its volume, and its particle number are fixed, and the triplet of variables E, V, and N completely specify the macrostate. When the system's not in equilibrium, for instance, its density may be changing, then things like density need to be specified. So in general, what we can do is, if we want to specify a general state when it may not be in equilibrium, we include an additional variable alpha, and that stands for all of the additional variables that we might need to deal with non-equilibrium states. So what we're going to do is we're going to let omega be a function of E, V, N, and alpha, and we're going to say that omega is the number of microstates specified by V and N and alpha, and whose energy lies between E and E plus delta E. Omega is what we called the multiplicity earlier. In this expression, we need to use a range of energy because it's difficult to specify or to measure the exact energy of a macroscopic system. And in fact, if we look ahead to quantum mechanics, we know that there's a relationship between energy and time in the uncertainty principle. And if we chose delta E to be 0, it would turn out that omega would be a mathematically badly behaved function, and that we would be badly behaved in the way that it's 0 most of the time, but at others it jumps to the degeneracy So we don't want that to happen. So it turns out that this quantity omega is actually insensitive to the size of delta E, and so any choice less than or equal to the actual energy makes omega a nice, well-behaved function. Omega can be called multiplicity. Sometimes it's called the statistical weight or the thermodynamic probability. I will most often call it the statistical weight. And for an equilibrium state, omega is just a function of EV and N because the alphas are fixed if the system is in equilibrium. So now what we're going to do is we're going to apply this idea to a simple system. And the simple system is called the system of spin magnets. Spin magnets can represent atoms in a chain and a host of other things. Essentially, a spin magnet is a simple system which can either have a spin pointed up or a spin pointed down, and we can designate them by up arrows and down arrows. And it turns out for a dipole, which is what a simple magnet is, for a dipole in an external field, the interaction energy is minus the dipole moment dot product with the magnetic field B. Dipoles tend to align with external magnetic fields. We're only allowing them to align up and down, and if the dipole is parallel to the field, the energy is minus MB. If it's anti-parallel, it's MB, and that means that there are two possible states, and the energy difference between the states is 2 MB. So what we'll do is we'll take n total dipoles, and we'll let n of them be parallel to the field. So then we can write a simple expression for the total energy. And you can see in this case that E has to be a function of n. So what we'll say is, in this case, the energy is a function of the field B, volume n, and both the total number of particles and the number parallel to the field. We're keeping the field constant. We'll keep big N constant. So in this case, the alpha variable is n, and it's completely determined by the energy. So if we look at a system like this, let's take 9 little magnets. So what we'll do is we'll choose n of them to align with the field, and or n equal 2 to align with the field, and we'll let the others be anti-parallel. So what we've got there are two states, both with only 2 little elementary magnets aligning with the field. We can distinguish them microscopically, but we can't distinguish one of those states from another macroscopically, because all we can measure is what the net magnetic field is. We would know that 2 magnets were aligned with the field, but we wouldn't know which 2. So in this particular case, the total number of microstates is 2 to the n, because each particle could be in one state or the other, and the number in the energy given by little n is the number of combinations of n large taken n small at a time, and so we can write that the multiplicity is given by that number of combinations. We can just look up the answer, and that gives us what the multiplicity is. And this is a number of states with n spin-ups. Simply by choosing the range of energy to be less than 2 MB, it turns out then the interval contains a single energy level, and that is the statistical weight in this particular case. If all of the, if little n is equal to big N, all of the spins are up, and we can write that the energy is simply equal to minus m multiplied by by Bn, and omega is equal to 1. That's the ground state, or the lowest energy state. If little n is equal to half of the total number of spin magnets, the total magnetization, big M, is equal to 0. The energy, total energy, is equal to 0. Omega itself is a maximum, and the system behaves as if there's 0 magnetic field. The most probable state is the most disordered one, and that's the one with the greatest multiplicity. In fact, we can state a version of the second law of thermodynamics based on that idea. And that's what we'll take up in the next video. So I'll end this one at this point.